Introduction to blockchain technology. Blockchain technology represents a revolutionary paradigm shift in how data is recorded and shared across networks. It is essentially a decentralized, distributed, and immutable ledger that records transactions in a secure and transparent manner. Each block in the chain contains a time-stamped batch of valid transactions, and once recorded, data in a block cannot be altered retroactively. This inherent security and transparency make blockchain highly disruptive across various industries, offering new solutions for trust and efficiency. Understanding its fundamental principles is crucial for anyone looking to navigate the digital future. This technology promises to reshape everything from financial systems to supply chain management, fostering a new era of digital trust. The core innovation of blockchain lies in its ability to establish trust among participants without the need for a central authority. This is achieved through a combination of cryptographic hashing, distributed consensus mechanisms, and a peer-to-peer network architecture. Participants on the network collectively validate and maintain the ledger, ensuring its integrity and resistance to tampering. This distributed nature eliminates single points of failure and enhances the overall resilience of the system. The transparency of transactions, while maintaining user privacy through pseudonymous addresses, is another key feature that differentiates blockchain from traditional databases. History and evolution of blockchain. The concept of blockchain technology can be traced back to the early 1990s with Stuart Haber and W. Scott Stornetter's work on cryptographically secured chains of blocks. Their research focused on creating a system where document timestamps could not be tampered with, laying theoretical groundwork for immutability. However, it wasn't until 2008 that the first practical application of this technology emerged. An anonymous entity known as Satoshi Nakamoto published a white paper detailing Bitcoin, a peer-to-peer electronic cash system. Bitcoin's launch in 2009 marked the birth of the first decentralized cryptocurrency and the first real-world blockchain. This event catalyzed a new era of digital innovation, demonstrating the potential of a trustless system. The initial implementation of blockchain was purely for financial transactions, but its underlying principles soon revealed broader applicability. Early adopters were primarily cryptographers and tech enthusiasts, but its influence quickly spread. Following Bitcoin's success, developers began exploring other applications beyond digital currency. Ethereum, launched in 2015 by Vitalik Buterin, introduced the concept of smart contracts, significantly expanding blockchain's capabilities. Smart contracts are self-executing agreements with the terms directly written into code, enabling programmable money and decentralized applications, dApps. This innovation transformed blockchain from a simple transaction ledger into a platform for complex, automated processes. The rise of Ethereum led to a boom in new cryptocurrencies and blockchain projects, each attempting to solve different problems or offer unique features. This period saw rapid experimentation and the development of various blockchain types, including private and consortium blockchains, catering to specific enterprise needs. The evolution continues with ongoing research into scalability, interoperability, and new consensus mechanisms, pushing the boundaries of what blockchain can achieve. Core concepts: distributed ledger. A distributed ledger is a database that is consensually shared and synchronized across multiple sites, institutions, or geographies. Unlike traditional centralized databases, there is no central administrator or data storage. Instead, each participant in the network maintains and validates an identical copy of the ledger. This decentralized approach ensures that all records are consistent and transparent across the network. Any update to the ledger must be agreed upon by a majority of the network participants, preventing any single entity from unilaterally altering data. The integrity of the data is paramount, as all copies must match. This architecture significantly enhances security and resilience against cyber attacks and data manipulation, making it highly robust. The distributed nature is a cornerstone of blockchain's trustless environment. Immutability is a critical characteristic of a distributed ledger, especially in blockchain. Once a transaction or data entry is added to the ledger and validated by the network, it cannot be changed or deleted. This is achieved through cryptographic hashing, where each new block contains a hash of the previous block, creating a secure and unbreakable chain. Any attempt to alter a past transaction would invalidate all subsequent blocks, making such an action immediately detectable by the network. This permanent and unalterable record provides a high degree of auditability and transparency, which is invaluable for applications requiring verifiable historical data. The immutability ensures a reliable and trustworthy record of all events, fostering confidence among network participants. This feature is particularly important in financial and legal contexts. Core concepts. Cryptography. Cryptography is the backbone of blockchain technology, providing the fundamental security and integrity required for decentralized systems. It involves techniques for secure communication in the presence of adversarial behavior, ensuring that information is protected from unauthorized access or alteration. Two primary cryptographic techniques are crucial in blockchain: hashing and public key cryptography. Hashing functions take an input, e.g., transaction data, and produce a fixed-size, unique output called a hash value or digest. This process is irreversible, meaning you cannot reconstruct the original data from its hash. Even a tiny change in the input data results in a completely different hash, making it an excellent tool for verifying data integrity. This cryptographic primitive ensures that once data is recorded, any attempt to tamper with it will be immediately evident. Public key cryptography, also known as asymmetric cryptography, uses a pair of keys, a public key and a private key. The public key can be shared widely, while the private key must be kept secret by its owner. These keys are mathematically linked, but the private key cannot be easily derived from the public key. In blockchain, the private key is used to digitally sign transactions, proving ownership of funds or data without revealing the private key itself. The public key is then used to verify this digital signature, confirming that the transaction originated from the legitimate owner and has not been tampered with. This system provides strong authentication and non-repudiation, meaning a sender cannot later deny having sent a transaction. This cryptographic mechanism is essential for securing user identities and transactions on the blockchain, ensuring both privacy and accountability. Core concepts. Consensus mechanisms. Consensus mechanisms are fundamental to blockchain technology, enabling all participants in a decentralized network to agree on the single true state of the ledger. Without a central authority, these algorithms ensure that new transactions are valid and added to the chain in an orderly fashion, preventing double spending and maintaining data integrity. Different blockchains employ various consensus mechanisms, each with its own trade-offs in terms of security, scalability, and decentralization. The choice of mechanism significantly impacts the network's performance and energy consumption. Achieving consensus is a critical challenge in distributed systems, and blockchain offers innovative solutions. These mechanisms are vital for the trustless operation of any blockchain network, ensuring reliability and preventing malicious actors from corrupting the ledger. Proof of work (POW) is the original consensus mechanism used by Bitcoin and Ethereum before its transition to proof of stake. In POW, miners compete to solve a complex computational puzzle, which is essentially finding a specific hash value. The first miner to solve the puzzle gets to add the next block of transactions to the blockchain, and is rewarded with newly minted cryptocurrency and transaction fees. This process is energy-intensive, but provides a high level of security, as altering past blocks would require redoing an immense amount of computational work. Proof of stake (POS) is an alternative, where validators are chosen to create new blocks based on the amount of cryptocurrency they stake as collateral. PoS is generally more energy efficient and can offer higher transaction throughput, as it doesn't require intensive computational competition. Other mechanisms like delegated proof of stake, DPoS, and proof of authority, POA, also exist, each tailored for different network requirements and decentralization levels. Blockchain architecture explained. Blockchain architecture is fundamentally designed around a chain of interconnected blocks, each containing a batch of transactions. When a new transaction occurs, it is first verified by the network and then grouped with other transactions into a new block. This block is then cryptographically linked to the previous block using a hash, forming a continuous chronological chain. Each block includes a timestamp, a reference to the previous block's hash, and the transaction data itself. This chaining mechanism ensures that the order of transactions is preserved and that any attempt to alter a past block would invalidate the entire chain, making the ledger tamper-proof. The architecture is inherently secure and transparent, providing a robust framework for recording data. Nodes are integral components of the blockchain network, acting as participants that maintain, validate, and propagate the ledger. Each node holds a full copy of the blockchain, enabling it to independently verify transactions and blocks. When a new block is created and validated by the consensus mechanism, it is broadcast across the peer-to-peer network to all other nodes. These nodes then add the new block to their copy of the blockchain, ensuring that the ledger remains synchronized and consistent across the entire network. The distributed nature of these nodes is what makes blockchain decentralized and resilient, as there is no single point of control or failure. Different types of nodes exist, such as full nodes, light nodes, and mining/validator nodes, each playing a specific role in maintaining the network's integrity and functionality. Types of blockchains. Blockchains are not monolithic. They come in various forms, each designed to suit different use cases and requirements. The primary distinction lies in their accessibility and permissioning models. Public blockchains, such as Bitcoin and Ethereum, are entirely open and permissionless. Anyone can join the network, participate in consensus, and view all transactions. This transparency and decentralization are their key strengths, fostering trust in a global, anonymous environment. However, they often face challenges related to scalability and transaction speed due to the need for broad consensus. Their open nature makes them ideal for cryptocurrencies and applications where maximum transparency and censorship resistance are paramount. The community-driven development and governance models are also defining characteristics of public blockchains, allowing for broad participation and innovation. In contrast, private blockchains are permission networks where participation is restricted and controlled by a single organization. Only authorized participants can join the network, validate transactions, and access specific data. While they sacrifice some decentralization, private blockchains offer significantly higher transaction speeds, better scalability, and enhanced privacy, making them suitable for enterprise applications. Hyperledger Fabric is a prominent example of a private blockchain platform. Consortium blockchains, also known as federated blockchains, are a hybrid model. They are permission networks where consensus is controlled by a pre-selected group of organizations rather than a single entity. This offers a balance between decentralization and efficiency, making them ideal for inter-organizational collaborations where a shared, trusted ledger is needed without full public exposure. R3 Corda is a well-known consortium blockchain. Each type serves distinct purposes, highlighting the versatility of blockchain technology. Bitcoin, the first blockchain. Bitcoin, launched in 2009 by the pseudonymous Satoshi Nakamoto, stands as the pioneering application of blockchain technology and the world's first decentralized digital currency. Its creation was a direct response to the global financial crisis of 2008. aiming to provide an alternative to traditional banking systems. Bitcoin operates on a public, permissionless blockchain, where all transactions are transparently recorded and verified by a network of participants, miners. The core innovation was solving the double spending problem without a central authority, ensuring that each unit of Bitcoin is spent only once. This was achieved through the proof-of-work consensus mechanism, which secures the network and incentivizes participation. Bitcoin's impact extends beyond finance, demonstrating the viability of decentralized networks and inspiring countless other blockchain projects. It laid the groundwork for the entire cryptocurrency industry. The Bitcoin network functions as a peer-to-peer electronic cash system. When a user sends Bitcoin, the transaction is broadcast to the network. Miners then collect these pending transactions and compete to create a new block by solving a cryptographic puzzle. Once a miner successfully finds the solution, the new block is added to the blockchain, and the transaction is confirmed. This process typically takes about 10 minutes per block. The total supply of Bitcoin is capped at 21 million, making it a deflationary asset. This scarcity, combined with its decentralized nature and robust security, has led to its widespread adoption as a store of value and a medium of exchange. Bitcoin's success proved that a global, trustless digital currency was not only possible, but could also thrive, paving the way for further innovations in decentralized technology. Ethereum smart contracts. Ethereum emerged in 2015 as a groundbreaking blockchain platform that significantly expanded the capabilities of decentralized technology beyond simple digital currency. While Bitcoin introduced the concept of a decentralized ledger for transactions, Ethereum introduced the concept of smart contracts. Smart contracts are self-executing agreements, with the terms of the agreement directly written into lines of code. They run on the Ethereum Virtual Machine, EVM, a powerful, Turing-complete runtime environment that allows developers to create and deploy complex, programmable logic. This innovation transformed blockchain from a mere financial ledger into a versatile platform for building decentralized applications, dApps. Ethereum's ability to host programmable logic opened up a vast array of possibilities, from decentralized finance, DeFi, to non-fungible tokens, NFTs, and beyond, fostering a rich ecosystem of innovation. Ethereum network functions as a global, decentralized computer. Developers can write smart contracts using programming languages like Solidity, which are then compiled into bytecode and deployed onto the EVM. Once deployed, these contracts are immutable and execute automatically when predefined conditions are met, without the need for intermediaries. This eliminates the risk of censorship, downtime, fraud, or third-party interference. Users interact with these smart contracts by sending transactions to them, triggering their execution. The network is secured by a consensus mechanism, which recently transitioned from proof-of-work, POW, to proof-of-stake, POS, with the merge. This transition aimed to improve scalability, reduce energy consumption, and enhance security. Ethereum's robust infrastructure and vibrant developer community continue to drive innovation in the blockchain space, making it a cornerstone of the Web3 movement. Smart contract development. Smart contract development involves writing self-executing code that runs on a blockchain, typically Ethereum. The most popular programming language for Ethereum smart contracts is Solidity, a high-level, object-oriented language specifically designed for implementing smart contracts on the Ethereum Virtual Machine, EVM. Developers use Solidity to define the logic, rules, and state transitions of a contract, including functions for sending and receiving cryptocurrency, managing data, and interacting with other contracts. Understanding Solidity syntax, data types, and control structures is fundamental for building robust and secure smart contracts. Tools like Remix IDE, Truffle, and Hardhat provide development environments, testing frameworks, and deployment pipelines to streamline the development process. These tools are essential for efficient coding, debugging, and deploying contracts onto the blockchain, ensuring they function as intended. The development lifecycle of a smart contract includes several critical stages to ensure functionality and security. First, the contract logic is designed and coded in Solidity. Next, it undergoes rigorous testing to identify and fix bugs, often using simulated blockchain environments. Security audits are also crucial, as vulnerabilities in smart contracts can lead to significant financial losses due to their immutable nature. Once tested and audited, the contract is compiled into bytecode and deployed to the blockchain network. After deployment, the contract's address becomes public, and users can interact with its functions by sending transactions. Post-deployment monitoring and potential upgrades, if the contract is designed to be upgradable, are also important considerations. Due to the immutability of deployed contracts, careful planning and thorough testing are paramount to prevent irreversible errors and ensure long-term reliability. Decentralized applications, dApps. Decentralized applications, or dApps, are applications that run on a decentralized network, typically a blockchain, rather than a centralized server. Unlike traditional apps, dApps are not controlled by a single entity, making them resistant to censorship and single points of failure. They leverage smart contracts to execute their logic, ensuring transparency and immutability of their operations. The back-end code of a dApp runs on a peer-to-peer network, while the front-end can be a standard web interface. This architecture provides users with greater control over their data and digital assets, fostering a more open and equitable internet. The core principle of dApps is to remove intermediaries, allowing direct interaction between users and the application's logic. This paradigm shift offers significant advantages in terms of trust, security, and user autonomy, driving innovation across various sectors. The characteristics of dApps include being open source, operating autonomously, having decentralized consensus, and utilizing cryptographic tokens. Being open source allows for community scrutiny and improvement, enhancing security and transparency. Their autonomous operation, governed by smart contracts, ensures that they run exactly as programmed without human intervention. The decentralized consensus mechanism of the underlying blockchain guarantees that the dApp state is agreed upon by the entire network, preventing manipulation. Cryptographic tokens are often used within dApps for various purposes, such as governance, utility, or value transfer. Examples of dApps span numerous categories, including decentralized finance, DeFi, platforms for lending and trading, NFT marketplaces, blockchain-based games, and decentralized social media. These applications are at the forefront of the Web3 movement, aiming to build a more decentralized and user-centric internet. The diversity of dApps highlights the vast potential of blockchain technology. Tokens and cryptocurrencies. Cryptocurrencies are digital or virtual currencies secured by cryptography, making them nearly impossible to counterfeit or double spend. Many cryptocurrencies are decentralized networks based on blockchain technology, a distributed ledger enforced by a disparate network of computers. Bitcoin is the most well-known cryptocurrency, serving primarily as a store of value and a medium of exchange. Other cryptocurrencies, often called altcoins, offer different features, consensus mechanisms, or use cases. The value of cryptocurrencies is determined by market supply and demand, and they can be traded on various exchanges. Their decentralized nature means they are not subject to government or financial institution control, offering a new paradigm for financial sovereignty. Understanding the distinction between different types of digital assets is crucial for navigating the crypto landscape. Tokens, while often used interchangeably with cryptocurrencies, typically refer to digital assets built on an existing blockchain platform, such as Ethereum. They represent a wide range of assets or utilities within a specific ecosystem. Utility tokens provide access to a product or service within a decentralized application, dApp. For example, a gaming token might be used to purchase in-game items. Security tokens represent ownership in an underlying asset, like real estate or company shares, and are subject to securities regulations. Stablecoins are a type of cryptocurrency designed to minimize price volatility by being pegged to a stable asset such as the US dollar or gold. They combine the benefits of blockchain with the stability of traditional assets. The proliferation of tokens has enabled new business models and funding mechanisms, such as initial coin offerings, ICOs, and decentralized autonomous organizations, DAOs. Each token type serves a distinct purpose, contributing to the rich and diverse blockchain economy. Wallets and keys. In the blockchain ecosystem, wallets are essential tools for managing cryptocurrencies and digital assets. Unlike physical wallets that hold cash, crypto wallets don't actually store your digital assets. Instead, they store the cryptographic keys, specifically the private keys, that prove ownership of your assets on the blockchain. A wallet provides an interface to interact with the blockchain, allowing users to send, receive, and monitor their holdings. It generates a pair of keys, a public key and a private key. The public key, derived from the private key, functions as your unique address on the blockchain, similar to a bank account number. You can share your public key freely for others to send you funds. Protecting your private key is paramount, as anyone with access to it can control your assets. Losing your private key means losing access to your funds forever, highlighting the critical importance of secure key management. There are several types of crypto wallets, each offering different levels of security and convenience. Hot wallets are connected to the internet and include web wallets, mobile wallets, and desktop wallets. They offer ease of access for frequent transactions, but are generally considered less secure due to their online nature and potential vulnerability to cyber attacks. Cold wallets, on the other hand, are offline storage solutions, providing a higher level of security. Hardware wallets, which are physical devices that store private keys offline, are a popular form of cold storage. Paper wallets, which are printed public and private keys, are another form of cold storage, though less common now. Seed phrases, typically a sequence of 12 or 24 words, are used to generate and recover private keys, serving as a backup. Regardless of the wallet type, robust security practices, such as strong passwords, two-factor authentication, and keeping seed phrases safe, are crucial for protecting digital assets. Understanding these distinctions is vital for secure participation in the blockchain space. Blockchain security. Blockchain technology is inherently designed with robust security features, making it highly resistant to tampering and fraud. The use of cryptographic hashing ensures that each block is immutably linked to the previous one, forming an unbreakable chain. Any alteration to a past transaction would change its hash, invalidating all subsequent blocks and immediately alerting the network. Decentralization, achieved through a distributed network of nodes, eliminates single points of failure and makes it extremely difficult for any single entity to control or corrupt the ledger. Consensus mechanisms, such as proof of work or proof of stake, further secure the network by requiring agreement among participants for new blocks to be added. These foundational elements contribute to blockchain's reputation as a highly secure and trustworthy system, providing a strong defense against many traditional cyber threats. The transparency of transactions also allows for public scrutiny, adding another layer of security. Despite its inherent strengths, blockchain networks are not entirely immune to security threats. Common attacks include 51% attacks, where a single entity or group gains control of more than 50% of the network's computing power in POW or staked assets in POS, potentially allowing them to manipulate transactions. Phishing scams and social engineering attacks target individual users to steal private keys or seed phrases, bypassing the blockchain's cryptographic security. Smart contract vulnerabilities, often due to coding errors, can lead to exploits and significant financial losses, as contracts are immutable once deployed. Best practices for enhancing blockchain security include rigorous smart contract auditing, using secure cold storage for private keys, implementing strong authentication methods, and staying informed about common attack vectors. Continuous vigilance and adherence to security protocols are essential for protecting assets and maintaining the integrity of blockchain applications. Education on these threats is vital for all participants. Scalability challenges. One of the most significant challenges facing blockchain technology, particularly public blockchains, is scalability. Scalability refers to the network's ability to handle a growing number of transactions and users without compromising performance. Current public blockchains like Bitcoin and Ethereum, prior to ETH2, have limited transaction throughput compared to traditional centralized payment systems like Visa. Bitcoin processes around 7 transactions per second (TPS), and Ethereum around 15 to 30 TPS, whereas Visa can handle tens of thousands. This limitation leads to network congestion, slow transaction confirmations, and high transaction fees during peak demand. The blockchain trilemma suggests that a blockchain can only achieve 2 out of 3 desirable properties: decentralization, security, and scalability. Most public blockchains prioritize decentralization and security, often at the expense of scalability. Addressing this challenge is crucial for mainstream adoption and broader utility of blockchain technology. Various solutions are being developed to address blockchain scalability. Layer 2 solutions, such as Lightning Network for Bitcoin and rollups, Optimistic and ZK rollups for Ethereum, process transactions off the main blockchain, Layer 1, and then batch them into a single transaction on Layer 1, significantly increasing throughput. Sharding involves dividing the blockchain into smaller, more manageable segments called shards, each capable of processing transactions independently and in parallel. This allows the network to process multiple transactions simultaneously, improving overall capacity. Other approaches include increasing block size, though this can impact decentralization, and developing new consensus mechanisms that are inherently more scalable. Sidechains, which are separate blockchains connected to the main chain, also offer a way to offload transactions. The ongoing research and development in these areas aim to overcome the scalability bottleneck, enabling blockchain to support global-scale applications and user bases. These innovations are vital for the future growth and widespread adoption of decentralized technologies. Interoperability solutions. Blockchain interoperability refers to the ability of different blockchain networks to communicate, share data, and transfer assets with each other. Currently, many blockchains operate as isolated silos, making it difficult for assets or information to move seamlessly between them. For example, a token on the Ethereum network cannot directly interact with an application on the Solana network without a bridge. This lack of interoperability hinders the overall growth and utility of the blockchain ecosystem, limiting the potential for complex decentralized applications that might require functionalities from multiple chains. As the number of specialized blockchains continues to grow, the need for seamless cross-chain communication becomes increasingly critical. Solving this challenge is essential for realizing the vision of a truly interconnected and composable Web3. Various solutions are being developed to address blockchain interoperability. Cross-chain bridges are one common approach, allowing assets to be locked on one chain and an equivalent wrapped asset to be minted on another. These bridges facilitate asset transfers, but can introduce security risks if not properly designed. Atomic swaps enable direct peer-to-peer exchange of cryptocurrencies between different blockchains without the need for an intermediary. Interoperability protocols, such as Polkadot's parachains or Cosmos's Inter-Blockchain Communication (IBC) protocol, are designed to create entire ecosystems where multiple blockchains can natively communicate and share security. These protocols aim to build a blockchain of blockchains, fostering a more integrated and scalable network. Other solutions include sidechains and relay networks. The goal is to create a seamless user experience where users can interact with any dApp or asset, regardless of which underlying blockchain it resides on, unlocking new possibilities for decentralized innovation and collaboration. Blockchain in supply chain. Blockchain technology offers transformative potential for supply chain management by enhancing transparency, traceability, and efficiency. Traditional supply chains often suffer from a lack of visibility, making it difficult to track products from origin to consumer and identify points of failure or fraud. Blockchain provides a shared, immutable ledger where every step of a product's journey can be recorded, from raw material sourcing and manufacturing to shipping and delivery. Each participant in the supply chain, such as suppliers, manufacturers, distributors, and retailers, can update the ledger with relevant information, creating a comprehensive and verifiable history. This transparency helps to build trust among stakeholders and provides consumers with greater confidence in the authenticity and ethical sourcing of products. The ability to quickly pinpoint issues like contamination or counterfeiting is a significant advantage, reducing costs and improving recall efficiency. Implementing blockchain in supply chains can lead to several key benefits. It significantly improves traceability, allowing companies to track individual items and their components in real time, which is crucial for quality control and compliance. The immutability of records ensures data integrity, preventing manipulation, and providing an auditable trail for regulatory purposes. Smart contracts can automate various processes, such as payments upon delivery or quality checks, reducing administrative overhead and speeding up transactions. This automation minimizes human error and increases operational efficiency. Furthermore, blockchain can help combat counterfeiting by providing verifiable proof of origin and authenticity for products. Companies like IBM, Food Trust, and Maersk's TradeLens are already leveraging blockchain to revolutionize their supply chain operations, demonstrating its practical utility. The technology fosters a more resilient, transparent, and efficient global supply chain, benefiting businesses and consumers alike. Blockchain in finance, DeFi. Blockchain technology is rapidly transforming the financial industry, giving rise to decentralized finance, DeFi. DeFi refers to an ecosystem of financial applications built on blockchain networks, primarily Ethereum, that aim to recreate traditional financial services in a decentralized, transparent, and permissionless manner. Unlike traditional finance, TradFi, where intermediaries like banks and brokers control transactions and services, DeFi protocols allow users to interact directly with smart contracts. This eliminates the need for trusted third parties, reducing costs, increasing speed, and enhancing accessibility for anyone with an internet connection. DeFi applications offer a wide range of services, including lending, borrowing, trading, and insurance, all without central oversight. The transparency of blockchain ensures that all transactions and contract logic are publicly auditable, fostering a new level of trust and accountability in financial services. Key components of the DeFi ecosystem include decentralized exchanges, DEXs, lending and borrowing protocols, stablecoins, and yield farming. DEXs allow users to trade cryptocurrencies directly from their wallets without a central custodian, reducing counterparty risk. Lending protocols enable users to lend out their crypto assets to earn interest or borrow against their collateral, all governed by smart contracts. Stablecoins play a crucial role by providing price stability within the volatile crypto market, facilitating transactions and acting as collateral. Yield farming involves strategically moving crypto assets between different DeFi protocols to maximize returns. While DeFi offers significant advantages such as increased financial inclusion, lower fees, and greater transparency, it also comes with risks, including smart contract vulnerabilities, impermanent loss, and regulatory uncertainty. Despite these challenges, DeFi continues to innovate, pushing the boundaries of what's possible in a truly open and global financial system. Blockchain in healthcare. Blockchain technology holds immense promise for revolutionizing the healthcare industry by addressing critical challenges related to data management, security, and interoperability. Healthcare systems often struggle with fragmented patient records, making it difficult for providers to access complete and up-to-date information, especially across different institutions. Blockchain can create a secure, immutable, and shared ledger for patient health records, allowing authorized parties to access and update information in real time. This enhances data integrity and reduces the risk of errors or fraud. Patients can also gain more control over their own health data, granting or revoking access as needed. The transparency and auditability of blockchain ensure that all access and changes to records are logged, providing an unalterable trail. This level of security and control is vital for sensitive medical information, fostering greater trust in data handling. Beyond electronic health records, EHRs, blockchain has numerous other applications in healthcare. It can streamline pharmaceutical supply chains, ensuring the authenticity of drugs and preventing counterfeiting by providing end-to-end traceability. Clinical trial management can benefit from blockchain's immutability, ensuring data integrity and transparency, which is crucial for regulatory compliance and research validation. Secure sharing of medical research data among institutions can be facilitated, accelerating scientific discovery while maintaining patient privacy. Identity management for healthcare professionals and patients can be enhanced, providing secure and verifiable credentials. Furthermore, blockchain can enable more efficient and transparent claims processing and billing. While adoption faces hurdles like regulatory compliance and integration with existing legacy systems, the potential for blockchain to create a more secure, efficient, and patient-centric healthcare ecosystem is substantial. It promises to improve patient outcomes and operational efficiency across the board. Blockchain in identity management. Blockchain technology offers a revolutionary approach to identity management, moving away from centralized systems towards a model of self-sovereign identity, SSI. Traditional identity systems rely on central authorities, governments, corporations to issue and verify credentials, leading to privacy concerns, data breaches, and a lack of user control. Self-sovereign identity, enabled by blockchain, empowers individuals to own and control their digital identities. Users can store their verifiable credentials, e.g., driver's license, academic degrees, on a blockchain-based wallet and selectively share specific pieces of information with relying parties without revealing unnecessary personal data. This minimizes the risk of identity theft and enhances privacy, as individuals are no longer forced to hand over their entire digital identity to every service they use. The immutability of blockchain ensures that credentials, once issued and recorded, cannot be tampered with, providing a high degree of trust in their authenticity. The implementation of blockchain in identity management involves several key components. Decentralized identifiers, DIDs, are globally unique, cryptographically verifiable identifiers that are not tied to any centralized registry. They are controlled by the individual and can be resolved to a DID document which contains public keys and service endpoints. Verifiable credentials (VCs) are tamper-proof digital credentials issued by trusted entities, a university issuing a degree, and stored by the individual. These VCs can then be presented to a verifier who can cryptographically confirm their authenticity against the issuer's public key on the blockchain. This system creates a secure, privacy-preserving, and user-centric approach to identity. Use cases range from secure login and KYC, know your customer processes, to digital voting and cross-border credential verification. Blockchain-based identity management promises to enhance security, reduce fraud, and give individuals unprecedented control over their personal data in the digital age. It represents a fundamental shift in how we perceive and manage identity online. Non-fungible tokens, NFTs. Non-fungible tokens, or NFTs, are unique cryptographic tokens that exist on a blockchain and cannot be replicated. Unlike cryptocurrencies like Bitcoin or Ethereum, which are fungible, meaning each unit is identical and interchangeable, each NFT has a distinct identity and value. NFTs are used to represent ownership of a wide range of unique digital or physical assets, including art, music, collectibles, virtual land, and even real-world items. The blockchain provides an immutable record of ownership and authenticity for these assets, solving the problem of scarcity and provenance in the digital realm. This allows creators to tokenize their work, creating verifiable digital scarcity and enabling new economic models for digital content. The rise of NFTs has opened up new avenues for artists, musicians, and content creators to monetize their work directly without intermediaries. The underlying technology of NFTs typically involves smart contracts on blockchain platforms like Ethereum. When an NFT is minted, a unique token is created on the blockchain containing metadata that points to the digital asset it represents. This metadata often includes information about the creator, a description of the asset, and a link to the digital file, e.g., an image or video. The ownership of the NFT is then recorded on the blockchain, and it can be bought, sold, or traded on specialized NFT marketplaces. Key use cases for NFTs extend beyond digital art to include gaming, ownership of in-game items and characters, metaverse, virtual land and digital wearables, ticketing, secure, verifiable event tickets, intellectual property, proof of ownership for creative works. The market for NFTs has grown exponentially, demonstrating the demand for verifiable digital ownership and the potential for new forms of digital commerce and cultural expression. Understanding NFTs is crucial for comprehending the evolving landscape of digital assets and their impact on various industries. Web3 and the metaverse. Web3 represents the next evolution of the internet, aiming to shift power from centralized corporations back to individual users. Built on decentralized technologies like blockchain, Web3 envisions a web where users own their data, control their digital identities, and participate in the governance of online platforms. Unlike Web2, which is dominated by large tech companies that monetize user data, Web3 leverages blockchain, cryptocurrencies, and NFTs to create a more open, transparent, and equitable digital ecosystem. This paradigm shift enables new forms of digital ownership, value transfer, and community-driven governance through decentralized autonomous organizations, DAOs. The core idea is to create a truly permissionless and trustless internet, where users are active participants and owners, rather than just passive consumers. This vision promises to unlock unprecedented levels of innovation and user empowerment, redefining our relationship with digital platforms. The metaverse is a persistent, interconnected virtual world where users can interact with each other, digital objects, and AI-driven entities in real time. Blockchain technology, particularly NFTs and cryptocurrencies, plays a crucial role in enabling the metaverse. NFTs provide verifiable ownership of digital assets within these virtual worlds, such as virtual land, avatars, and wearables, creating a real economy. Cryptocurrencies serve as the native currency for transactions within the metaverse, facilitating buying, selling, and earning. Blockchain also enables secure digital identity and interoperability between different virtual environments, allowing users to carry their assets and identities across various metaverses. The combination of Web3's decentralized principles and the immersive experiences of the metaverse was creating a new digital frontier. This convergence is fostering a new era of digital ownership, commerce, and social interaction, blurring the lines between the physical and virtual worlds. The potential for economic and social transformation is immense. Regulatory landscape. The regulatory landscape surrounding blockchain technology and cryptocurrencies is complex, rapidly evolving, and varies significantly across different jurisdictions. Governments and regulatory bodies worldwide are grappling with how to classify, govern, and oversee these nascent technologies. Key areas of regulatory focus include consumer protection, anti-money laundering, AML, combating terrorist financing, CTF, taxation, and financial stability. The decentralized and borderless nature of blockchain poses unique challenges for traditional regulatory frameworks, which are often designed for centralized entities within specific national boundaries. Regulators are attempting to strike a balance between fostering innovation and mitigating risks associated with illicit activities, market manipulation, and investor fraud. This uncertainty creates both opportunities and hurdles for businesses and individuals operating in the blockchain space, requiring careful navigation of legal requirements. Understanding the current regulatory environment is crucial for compliance and sustainable growth. Different jurisdictions have adopted varying approaches to blockchain regulation. Some countries have embraced a progressive stance, creating regulatory sandboxes and clear guidelines to encourage innovation, while others have implemented stricter bans or highly restrictive frameworks. For example, some nations classify cryptocurrencies as commodities, others as securities, and some as property, each classification carrying different legal implications. The regulation of stablecoins, DeFi protocols, and NFTs is also a growing area of focus, with discussions around consumer protection and systemic risk. International cooperation is becoming increasingly important to address the global nature of blockchain. Businesses operating in the blockchain space must conduct thorough legal due diligence and adapt their operations to comply with local and international regulations. The ongoing development of comprehensive and harmonized regulatory frameworks will be critical for the long-term maturation and widespread adoption of blockchain technology, providing clarity and fostering trust among users and institutions. Navigating this evolving landscape requires continuous monitoring and adaptation. Future trends in blockchain. The blockchain landscape is continuously evolving, with several exciting future trends poised to shape its next phase of development. One significant area of research is quantum resistance. As quantum computing advances, there's a theoretical risk that it could break current cryptographic algorithms, potentially compromising blockchain security. Researchers are exploring post-quantum cryptography to develop new algorithms that are secure against quantum attacks, ensuring the long-term integrity of blockchain networks. Another trend is the development of more sustainable and energy-efficient consensus mechanisms, moving beyond the energy-intensive proof of work. This includes further advancements in proof of stake and exploring novel approaches to reduce the environmental impact of blockchain operations. These innovations are critical for addressing environmental concerns and improving the public perception of blockchain technology. Further advancements in scalability and interoperability solutions will also be crucial for mainstream adoption. We can expect more sophisticated Layer 2 solutions, sharding implementations, and cross-chain protocols that enable seamless communication and asset transfer between diverse blockchains. The integration of blockchain with other emerging technologies, such as artificial intelligence, AI, and the Internet of Things, IoT, is another powerful trend. AI can enhance blockchain analytics and smart contract auditing, while IoT devices can leverage blockchain for secure data exchange and automated transactions. Decentralized autonomous organizations, DAOs, are expected to mature, offering new models for governance and collective decision-making. The expansion of real-world asset tokenization, where physical assets are represented as NFTs on a blockchain, will also gain traction. These trends collectively point towards a more interconnected, efficient, and impactful blockchain ecosystem, driving innovation across industries and redefining digital interactions. The future of blockchain promises a more integrated and powerful digital infrastructure. Building a blockchain project involves a structured approach. from conceptualization to deployment and maintenance. The first step is to clearly define the problem you are trying to solve and determine if blockchain is the appropriate solution. Not every problem requires a blockchain, and understanding its strengths and limitations is crucial. This involves identifying the core use case, target users, and purpose, and the specific benefits blockchain will bring, such as decentralization, immutability, or transparency. Next, choose the right blockchain platform, considering factors like scalability, security, developer community, and cost. Popular choices include Ethereum, Solana, Polkadot, and Hyperledger Fabric, each offering different features and ecosystems. A well-defined problem statement and platform selection are foundational for a successful project, guiding subsequent development efforts. This initial planning phase is critical to avoid common pitfalls and ensure alignment with project goals. The development phase typically involves designing the architecture, writing smart contracts, and building the user interface. Smart contracts, often written in Solidity for Ethereum-based projects, encapsulate the core logic and rules of the application. Rigorous testing and security audits of these contracts are paramount to prevent vulnerabilities that could lead to significant losses. Front-end development involves creating a user-friendly interface that interacts with the smart contracts on the blockchain, often using libraries like Web3.js or Ethers.js. After development, the project undergoes deployment to the chosen blockchain network. Post-deployment, continuous monitoring, maintenance, and potential upgrades are necessary. Engaging with the community, gathering feedback, and iterating on the product are also vital for long-term success. Building a blockchain project requires a multidisciplinary team with expertise in cryptography, distributed systems, smart contract development, and cybersecurity, emphasizing the complexity and specialized nature of this field. Career opportunities in blockchain. The rapid growth and adoption of blockchain technology have created a burgeoning job market with diverse and exciting career opportunities. As more industries recognize the transformative potential of decentralized solutions, the demand for skilled blockchain professionals continues to outpace supply. This creates a highly competitive and rewarding environment for those with the right expertise. Roles range from highly technical positions in development and cryptography to more business-oriented roles in strategy and consulting. The industry is still relatively young, offering ample opportunities for individuals to specialize, innovate, and make a significant impact. A strong understanding of blockchain fundamentals, coupled with specialized skills, is highly valued. The global nature of blockchain also means that many roles can be remote, offering flexibility and access to a worldwide talent pool. Key career paths in blockchain include blockchain developer, focuses on writing smart contracts, building dApps, and developing core blockchain protocols. Blockchain engineer, works on the underlying infrastructure, network architecture, and integration of blockchain solutions. Smart contract auditor, specializes in identifying vulnerabilities and ensuring the security of smart contracts. Blockchain consultant analyst, advises businesses on blockchain strategy, implementation, and market trends. Cryptocurrency trader analyst, focuses on market analysis, trading strategies, and understanding digital asset economics. UI/UX designer, Web3, designs user-friendly interfaces for dApps and blockchain platforms. To succeed in these roles, a combination of technical skills, e.g., Solidity, Rust, cryptography, distributed systems, and soft skills, e.g., problem-solving, adaptability, communication, is essential. Continuous learning and staying updated with the latest advancements are crucial in this fast-paced industry. The blockchain sector offers a dynamic and innovative environment for career growth and professional development.